Welcome back. We're now embarking on our second major topic in the region's physics. And the second major topic is on electricity and magnetism. And this is going to primarily focus on charges and the forces exerted between them and how we can use that. But just know that this is all the foundation of our modern society. Our modern society uses electricity for everything. And this, the physics that we're going to learn about, is the foundation for all of that. So without this, we would have none of our modern things. We wouldn't have a computer you're staring at now. We wouldn't have our lights. We wouldn't have our phones or anything like that. So it's kind of important how it relates back to our original lives. So we're going to start off with Chapter 17. And we're going to look at the very basics of charges and the forces between them and how those things exert forces on each other. So in Chapter 17, it's all electric forces and fields. And we're going to start off with a little history. And we're going to start about talking about the Greeks. And the Greeks were the first set of people to discover the electrical charges and their properties. And basically, in about 600 BC or so, they saw that if you took this rock called amber, if you've ever seen Jurassic Park, you've probably heard of amber. It's fossilized tree sap, dino DNA can be found in it, that kind of thing. But if you rubbed it on a cloth, it had the ability to attract other objects. And it actually behaved a lot like a magnet, which they already knew about, which we'll talk about in later chapters. But the difference between that and a magnet is that this amber would attract everything, whereas a magnet would only attract certain things. And so they knew this a little bit, and so they did some foundations and some recording of the discovery. Okay. Then we went through the Dark Ages and everything else when nobody really did much of anything scientifically. And until we got to about the 16th century with William Gilbert. William Gilbert gets credit because he was the first person to do scientific experiments with this. And then Abe was able to, classify not just amber, but other things that if you rub them with certain things would have these attractive properties or these repulsive properties, as it turned out too. And he named everything that had these properties called electrons, and I'll highlight that, which actually came from the Greek word electron. And electron is amber in Greek. And so William Gilbert gets credit for doing this first scientific study of all this. We then, what Gilbert came up with is said that every electric object had the ability to attract other objects, not just electric objects, but other objects, any other object, when rubbed with a cloth or a fur. And so when this happens, he stated that this object obtained an electric charge. And so he was the first person to say that it would, basically when you did this rubbing thing, this thing would get an electric charge. And because these charges were not in motion, this is the foundation of static electricity. So static, that means the stationary. So he said that these charges, once you transfer them to the electric object, that they would then be stationary. Okay, so we have stationary charges built up on the object. Electric, I'll put it into the electric object. And he scientifically recorded his results. Well, the next person that came along to do some investigation, this is Ben Franklin. And you may have heard of the story of Ben Franklin flying the kite in the lightning storm and being able to get an electric shock off the key that he put on there. Okay, and that turns out to be it was a true statement. He actually did attempt this. He was not the first person to attempt this. He was one of the first people to attempt it and live, which is why he's, gets credit for this. Okay, but he was able to now examine these a little bit more carefully. And he decided or discovered that there are actually two types of charges. And so what he said, and he experimented with rubber and glass, and he stated that the charge acquired by a glass rod when rubbed with silk was called a positive. And the charge acquired by a rubber rod when rubbed with fur is called the negative. And he noticed that they had opposite charges. Now, a little side note on this is the fact that they, at this point in time, had no concept of protons, electrons, neutrons, anything like that. You know more chemistry than Ben Franklin did. What he thought, what he imagined this thing was, is that there was this fluid around everything called the ether. And that when you rubbed a glass rod with silk, that the silk would give up some of its ether and transfer that into the glass rod. And so the glass rod had a positive because it was gaining, so positive because it gained ether. Write that out. That's, yeah, an ether. And the rubber rod was negative because it lost this ether. And again, it was this invisible fluid that was around us. And what he's looked at was the glass rod was like a vessel which held it. And the rubber rod vessel, everything held a certain amount of ether. And then when you rubbed it, you were able to transfer that fluid back and forth. Turns out he screwed up and he made a mistake here. And we'll talk about it later on. But he actually kind of messed this up for everybody. Okay? Now, what Ben Franklin looked at was that there were actually three possibilities as to why these things would gain or lose that ether. Okay? And so he knew, we're going to look at it in terms of our modern thing and just explain it. But if you were to take this, and I'll draw this out really quickly, but if this is your rod, I'll put it as rod, and this is your fur, okay? The first possibility is that the rod would gain, or sorry, let's do glass rod. Oh, you know what? Let's do glass rod and silk. Let me erase this. I'll make this silk. There you go. And so what he initially, there's three possibilities. The first is that the silk would give up its positive charges. The rod, and I'll put these in purple, would give up its negative charges. And so the rod would gain the ether, okay? The silk would lose that ether, and that's why they'd have those charges, okay? That's one possibility. The second possibility, put a rod, I should put a number 1 here. Number 1, number 2, here's our silk, was that only the positive charges would be moving. And this is what Ben Franklin thought. This was his thought, that the silk was giving up its ether to the rod. And so the rod would have an abundance of the positives. The silk would lose the positives, lose its ether. And so the rod would have a positive charge and the silk would have a negative charge. Or the third possibility, number 3, number 3, rod, there we go, and silk, was it just the rod would give up its negatives. And so the rod would still have too many positives, the positive charge still could have too many negatives to become negatively charged, that kind of thing. So just as a side note, this is what Franklin thought. And claimed. And turns out of all the ways, this is the one that's wrong. So turns out that we now know that positives do not move. We know that in reality, this is truth for solids. In solids, only the negatives will move. Okay, and that's because of valence electrons, and we'll talk about that a little bit more. In liquids, and I'll circle this in the red, okay, this is for fluids. So it doesn't really pertain to this particular thing, but if you're talking about fluids exchanging charges, both positives and the negatives move. But Ben Franklin chose this one. I'll put it in a nice little red here. This is what he thought, okay? Which turned out to be completely wrong. We now know it's number 3. So continuing on, we now have able, and I'm going to go a little further, jump ahead of Ben Franklin. We know that negative charges are carried by electrons. We know that positive charges are carried by protons. And we now know from our knowledge of chemistry and what we've discovered is that the negative charges that move. And so we talk about the theory that relates matter and electricity as being the electron theory because we know that it's the electrons that actually move. Now, there is a link on your slide that you can click on this because I'm dating myself here. I am old, very old. But I've always talked about this as the fact that like charges repel and opposite charges attract. as being the Paul Abdul rule. And there's a video you can watch it. If you remember Paul Abdul, she used to be a judge on American Idol. She used to have her own TV reality show. Before that, she used to be a singer, performer, and before that, a Laker girl. She was actually a Laker cheerleader. But I go back to her song, Opposites Attract, to try to remember. And that's why I call it the Paul Abdul rule. And if you click on the link, you can watch the video. It's fairly entertaining for a late 80s video. So again, like I said, I'm dating myself here. Okay, but what we need to remember is the key thing here is that opposites attract. And that's the whole point. Attract, there we go. Okay, and you need to know that likes repel. And I've got it written here. So electrons attract protons, but protons hate other protons, and electrons hate other electrons. Okay. And so I've got this picture here. You don't have this picture, but you can draw that in. So again, you can see the two positives repelling each other, and the positive negative attracting each other. Okay. Now, when Ben Franklin was charging those objects, when William Gilbert was charging, when those Greeks were charging objects, okay, they were able to transfer those charges. Ben Franklin thought it was ether that was being transferred. We now know it's charges. Well, how is an object charged? In order to answer this, we need to understand a tiny bit of chemistry. And basically, we need to remember, and you should know this by now from your 8th grade physical science or chemistry, is that atoms are made up of positively charged protons along with negatively charged electrons, along with neutrons, okay? But the electrons are on the outside of the atom, and the protons are embedded in the nucleus. So if you were to look at an atom, you'd have a proton and another proton and maybe a couple neutrons in there, which we'll put in green. Neutron, neutron. We'll just go with helium for right now. And then you'd have the electrons, which I'll put in purple, on the outside. And so when that object is rubbed, again, this is just a helium, you can't rub helium, but you get the idea. But when the object is rubbed, what happens is some of these electrons, these valence electrons, are ripped off. And so it's the transfer of those electrons off of your atom, that allow you to transfer that charge from spot to spot. And so it's actually the electrons that move. Now, the last thing for today is that I want to tell you there is another conservation law, and that's the law of conservation of charge, or I'll put it as LOCO-C, law of conservation of charge, which states that the total amount of charge in any process must remain constant. Okay? And so when you rip charges off of something and you put it onto something else, the total charge of the system is going to stay the same. You are just transferring them from spot to spot. Charge cannot be created nor destroyed, only move from spot to spot. So we'll do some investigating. We'll do some further explanation. I'll show you some demonstrations on this tomorrow. Okay? But this is just the foundation of these charges. So that's it for today. Everybody have a great day. We'll see you later. Bye.